So far we did we started from basic equation on Fourier space, and we learned how to compute the nonlinear term and the viscous term. Viscous term was easy, but the nonlinear term is tricky. It just involves a lot of algebra. So it turns out there is a basis called Kriya-Haring basis. So there are two people, Kriya and Haring. So it was some 40 years back. This is not new basis. So Kriya is French and Haring American, and they made this basis, which is quite easy. So this is what I will do today. So what is the advantage of this basis? So I will first describe right now in 2D and 3D both. So we can construct equations in 2D as well as in 3D. So it is convenient to express the incompressible flows. I will show you how. We can derive equations of motion easier. So algebra is reduced, and so there is something called helical basis for this screw like fields, that is easier expressed in helical basis, which is constructed using Kriya-Haring basis. So these bases are used for making the helical basis. So this we will study this later. Okay, so let us start on showing you how to construct this basis. Okay, so we will first work with 3D. So this is a vector. So we have wave numbers, no? So wave number is a vector k. So this is a wave vector k. So please pay attention to this figure. Now along the direction of vector k, I make E3. So it will have 3 components, but this is variable. So you will find that x cap, y cap, z cap are fixed bases, but here the basis vectors will move along with k. So these are like radial polar coordinate, okay, but it is different, it is not radial polar. So my E3 along k cap. Now perpendicular to k. So this one thing, this E3 is easy. Now we need an anisotropy some direction. It need not be anisotropy direction, some direction we need. If there is anisotropy like magnetic field or rotation, you can choose the rotation axis to be n cap, this n cap. Okay, I need one more vector, but choice is yours. For MHD or for rotation, we can choose n cap along rotation axis, but it is not mandatory. You can choose n cap in any direction you like. Now given n cap and k cap, I construct E1 like this, k cap. So these are unit vectors, okay. Cap means unit vector, no. So length 1, but direction along k. So k cap cross n cap divided by modulus of this. So which direction will that be in this figure? So k cross n is basically take this k vector and cross it, go towards n cap. So it will be along E1. So it is perpendicular to the plane formed by n cap and k cap. Cross product is, so there is a plane here, this plane, and is perpendicular to that plane, and is along E1. So this is the first vector. Now what is E2? So it is cyclic. So 1, 2, 3. Okay, so the cyclic, you want everybody understands 1, 2, 3. So E1 cross E2 is E3, 2, 3 gives you 1, and 3, 1 gives you 2. So E3 cross E1. So do cyclic, 1, 2, 3, just go around. So E3 cross E1 gives you E2. It lies in the plane, right? So E3 cross E1 will be perpendicular to both E3 and E1, and is in the same plane, which is this plane. Now so velocity vector for incompressible flows, we know that is k dot uk is 0, correct. So uk must be lying where? Perpendicular to k vector. So it will lie in the plane formed by E1 and E2 vectors. So which is the natural basis for you for expressing velocity vector? E1 and E2. So we do not need to worry about 3D vectors now, we just need to worry about 2D vectors. So, my velocity field is E1 plus U2 E2, and U3 the velocity has no component along E3. So, U3 is 0, just straightforward, right, and this is very, I mean this is straightforward, but it is very useful. So, you can use this to solve quite a bit of problems in a less number of steps. So, any questions on this? So, please keep in mind that we need another vector n cap. So, k cross n cap gives you E1, of course you divide by magnitude, and E2 is E3 cross E1 is E2. Now, given x cap, y cap, z cap, or given ux, uy, uz, you can construct u1, u2 and vice versa. It is like very similar to what you do for spherical polar to Cartesian, or Cartesian to spherical polar or cylindrical. So, these are another basis vector, but we can do it that way. Now, please remember it is in Fourier space, it is not in real space. So, there is no gradient, there is no curl, but you have k cross. So, there will be a lot of cross product with k, dot product with k, but it is not in real space, it is in Fourier space. Now, we start looking at energy. So, what about energy? Energy is u star, I forgot dot. So, u star k dot uk. So, what will that be? So, by the way, please remember E1 and E2 are perpendicular to each other. If I take a complex conjugate of this one fully, u star k vector is equal to u1 k E1 k star. So, E1 is a real vector, right? Here E1, E2, E3 they are all real vectors. So, if I take a complex conjugate I get same thing, but U2 is also complex. So, U2 star, but E2 is a real vector. Now, if I take a dot product of these two, E1 dot E2, E1 dot E1 is 1, E2 dot E2 is 1, but E1 dot E2 is 0. So, you can easily see that you will get these terms, right. So, kinetic energy is just half U1 mod square plus half U2 mod square. Now, let us try to understand how to convert this in real space. Okay, some of these symbols are not transported properly. So, this is x, y, z, x, y. Okay. So, this k perp. So, no, there is just too many problems in this. Okay. So, this k vector, this conversion from Mac to Windows. Okay. So, k vector. So, this 3D, this one is 3D, right? See the same stuff. So, now my plane is this yellow plane, this one. Now, E3 is along k direction, E3. What about E1? E1 is perpendicular to the plane towards me, right. So, if I see from the top is going like this clockwise E1. So, please keep this in mind. You look at this picture several times and we will need it quite often. So, this is E1 and E2 is E3 cross E1 gives you E2. So, this is E2. Now, so what about z component of uk? So, my vector is uk, velocity vector. I want to find out what is z component. So, which will give you z component? Remember, my u is only along u1 and e2. So this E1 has, does u1 has any z component? u1 is along x and y, right? u1 is azimuthal, so it has no z component, but u2 has z component. This is u2 is along this. So, what is this angle? So, this angle is zeta. So, zeta is polar angle for me. So, in this book we will always find zeta as polar angle. I am reserving theta for temperature, okay. So, this is for convection. So, that is why we are not using theta. So, zeta and phi. So, phi is the azimuthal angle. So, this angle will be 90 minus zeta. So, this is zeta. So, this angle is zeta. So, this is 90 minus zeta. So, u2 cos 90 minus zeta will give with a minus sign, because my uz is upward, but this is downward. So, that is the z component, okay, minus u2 sin zeta, fine. Now, what about x component and y component? So, this k perp. So, my velocity vector I am projecting it down now on the xy plane. Now, by the way, there is no z component anymore. Now, I only left is if after I remove this, I only left with x and y components. Okay. So, now my u1 vector will be along this, okay, and my u2 vector will be along this, but how much is coming along this? Cos zeta. Cos zeta is the remaining part, because this part is sin zeta. So, this part is cos zeta. So, cos zeta is there. Now, take component of these. So, this u1, so I have drawn it here. So, basically E1, you take the component of E1, u1 is not a vector, u1 is a number. So, this angle is phi. So, what should be this angle? So, this 90 minus phi, so this phi. So, along x direction will be minus E1 cos phi. No, so that is y direction. So, x component is in that direction, okay. So, sin phi, this sin phi. So, u1k sin phi will be this one, u2 u1 cos phi with a minus sign is this one, this one. Now, this is u2 cos zeta, okay, u2 cos zeta. Now, I have to take a component again, cos phi and sin phi. So, these are this, okay. So, we need, well, especially in our computer code, we need to transform. So, if you solve in u1 and u2, you will need to find ux in uy and uz. So, you use this transformation, okay. Now, once you have this cos phi sin phi, you can express them in terms of kx and ky kz. So, what is cos phi? So, this angle is phi. So, this vector is k perp. So, cos phi is, so yeah, so basically cos phi is this one, kx by k perp, right. So, this kx. So, ks by k perp gives you cos phi. This is sin phi, ky by k perp, right, this one. This one is ky. So, ky by k perp is sin phi. Sin zeta is this k perp. So, this vector is k perp. So, this is k perp. K perp by k vector will give you sin zeta. Okay. So, this algebra is straightforward, but you should know how to convert this. Okay. It is very much similar to spherical polar coordinate, but they are not spherical polar coordinate. Spherical polar coordinate is tangential. Well, there is some similarity, but yeah, there is some similarity, because u2 is like u theta. Yeah, actually there are some u theta. Yeah, in fact they are very similar, they are very similar. Yeah. So, u phi is like u1. So, it is like spherical polar, but yeah, this is called Kriya-Haring for fluid dynamics, okay, and it is in Fourier space, okay. In fluid dynamics, u1 is called toroidal. So, toroidal is like phi, and u2 is called poloidal. So, polar angle, poloidal, okay. So, this is more commonly used word, poloidal, u2, u1 is toroidal, and there are real space equivalent, but I will not discuss that in this course. Okay. So, what about vorticity? You can write vorticity in terms of u1 and u2. So, vorticity vector is I k cross uk. Okay. So, k vector, so you can take a cross product. So, now I want to write k as k e e3. So, you have to use the Cray Herring, do not use x, y, z. So, K has only component along E3 and U1 has component along U1 and U2, U1 E1 plus U2 E2. So, what is E3 cross E1? Plus E2 or minus E2? Plus cyclic, no, 3 1 2. So, that gives you U1 E2 and E3 cross E2 minus E1, this going anticyclic, so put a minus sign. So, minus U2 E1. So, this is what I got. So, IK U1 will be minus U2K and E2 component is U1K. So, they are flipped with a minus sign. Now, we can construct cross helicity. So, I take the dot product of this with U star K and then of course take the real part. Okay. So, if you do the algebra, which is just straightforward, so there is a complex conjugate here. No? Okay. So, I will not do every step, but you will get this imaginary part of U1 star K U2 K. So, what does it tell you? It tells you that both U1 and U2 must be non-zero, and so if both of them are real, what happens? Because both of them real, it will be imaginary part will become 0, no. So, both of them real is 0. One should be, well, I mean both of them complex, then you take the part, but it should be, if one is real, other must be imaginary, okay, and if other is real, then first one is imaginary. So, you need a combination which gives you non-zero. It is very similar to what we saw that time, U real multiplied by U imaginary. Yeah, so we need, so U1 and U2, at least one of them, if you have pure real, pure imaginary, both of them, then is 0. And that is basically telling you that one is sine, other one is cos. Okay, so that is what is the thing. So, this is why circular polarization. So, both of them cannot be cosine or both of them cannot be sine or combination, of course. So, we can write U1 as U1 is a complex number. So, I can write U1 as this mod U1 e to the exponential I phi 1. So, if I substitute it in this expression, what do I get? K mod U1 mod U2 sin phi 2 minus sin phi 1. Okay. So, the phase of U1 and U2 must not be in the same direction. So, in fact, we need this phi 2 minus phi 1. So, any angle, so it need not be 90 degrees. So, if it is cosine and sine, then it is 90 degrees, but it could be any angle which is not 0 for helicity. And this is indeed connected with elliptical polarization. So, if there are 90 degrees, then circular polarization, which I am not doing it in this class, I think I will skip, maybe helicity I will do it later, well maybe I will see, I will do it later. So, we will discuss about helical waves a bit later. So, these are, if 90 degrees, then it is circular polarization, if it is not 90 degrees, then it is called elliptical polarization, and if that 0, then it is planar polarization with no helicity. Okay. So, any questions so far? So, let us see equation of motion. Now, this is where the more difficult parts are coming. So, we can do what I did for equations of motion. So, we are computing what? You are computing ux, uy, uz last time, no, or uk vector. So, I had to compute nx, nk vector, then compute pressure. So, we did lot of algebra in the last class. So, let us see whether we can simplify that. So, now, so I have only two components for velocity field alpha 1 and 2, E1 and E2. So, I take the component of velocity vector along E1 and E2. So, this alpha can take values 1 and 2. So, take the component along E1 or E2 and you will get U1 and U2. So, this is nonlinear term, I take the component along this one, this force and this viscous term. What happens to the pressure?
alpha is 3, then we can get rid of that.
Okay, if you put alpha is 3, but what about du3 by dt? 0. So there is no component of velocity along 3. So precisely take the component along this thing. So this I get 0. But nonlinear term can have component along 3. Okay. So this is what, when you do this calculation, you find that nonlinear term has component along U3, E3, that will be balanced by pressure and force together. So I take the component of these equation along E3. So I have this force, external force, the pressure has full component along E3 because k vector p, no. So k vector p, so k vector is along E3, so it has, that is why it is ikpk, and this is a nonlinear term. I take the component along E3, so it is nu comma 3. So this means nu dot E3, by the way, this is what it means. And my notation, please remember, my nk is u dot grad u Fourier transform of this. That is my notation. I always, so when I take it to the right hand side, that this minus sign is coming, this minus sign. So remember, please, this is my definition of nk. So is that fine? So I can compute pressure in Kriya Haring by this formula. Just invert this and you will get that. Now let us also look at parity transformation. So this is a part is also tricky. So I am just going to show you the picture. So this is my k vector. So what is parity? Parity is minus k. So you change k to minus k, that is called parity transformation. Okay. So k to minus k. So for k vector, so I think this picture is, well, maybe you can draw it, but just focus on the slide. Huh? So E1, so n cap is this way, so my plane is this. So E1 is perpendicular to the plane for k vector towards me, away from, I mean upward to the plane like this. E2 is downward like that. So E3 cross E1 is E2. Okay. So this is it. Now for what happens to minus k? What is the direction of E1? So k cross n. So now it is minus k. So minus k. So this right hand rule, not right hand rule, minus k cross n. So it's going into the plane, into this plane of paper. So that is why E1 is like this, into the plane. So E1 for k vector, this k, and E1 for minus k, are they in the same direction? They are not. They, in fact, they are opposite direction. So this is one problem with this unit vectors which are changing with k. A radial polar coordinate, that is one problem. My unit vectors are changing. Okay. And Cartesian is nice that way. Cartesian does not change. My x cap remains x cap wherever my k vector moves. But here my k vector goes to minus k, my E1 changes. And by the I was calculating, I spent 1 week to figure this, where I had a problem and the origin was sitting here. So it simply did not occur to me that my k vector, my E1 is negative. So one has to be careful with this. What about E2? E2 changes or does not change? So E3 is for minus k is like this. So E3 cross E1. So E3 cross E1 will give you E2 in that direction. So E2 does not change. E2 is in the same direction. So my E3 has changed. E3 has opposite. My E1 has changed, but E2 does not change. It can't be, right? If two of them changes, third one can't be. Otherwise, there will be a minus sign problem. So these are the transformation rules. So E1 is If I go to from q to minus k, I get a minus sign. E2 does not change and E3 does not change. E3 changing, sorry, E3 change. E2 does not change. Okay, and so my remember my u of vector k is equal to u1 E1. So I should write k plus u2 k E2 k. By the way, these are scalar numbers, complex numbers. You should not write vector on u1 and u2. What about u star k? Is just u1 star k E1 k. I should write, in fact I should write k here, plus u2 star k E2 of k. What about u of minus k? That is same as u star k, right? Why reality condition is not to be broken. So these two are equal, yes or no? So u of minus k is now going to come from here, which is u1 of minus k E1 of minus k plus u2 of minus k E2 of minus k. Okay. So these two are equal. So what happens to the relationship between these two? So u2 of star k, so actually I have the next slide. So u2 of minus k is same as u2 star k, right, from here. What about u1 of this relation? There is a minus sign because these are connected by minus sign. So this is this relation. In fact, this is what I spent 1 week to figure out this in my calculation. So there is a minus sign. So u1 of minus k with u1 star k. Okay. So these are very useful when I am calculating things. I am calculating some equations on helicity or some field theory. Okay. In 2D, so this is for 3D, but when I am working with 2D, then I do not need both the components, just one component. But which one should I choose? E1. Okay, good. So idea here is that, so this is 3D. Now I push this k vector on the equatorial plane, this plane. So my u2 will be pointing downward along minus g. So what happens here? So u2 will point like this and u1 will point towards me clockwise. Okay. So it is in the yellow elliptic plane. So my k vector, so is that fine? So u2 for 2D fields is not important because my plane, my velocity, so you see, so this is my x and y. My k vector is like this, my velocity vector will be like this. So it has component along only along E1. So remember z is here or n cap, z cap or n cap is here. So my E1 will be in that direction. E1. What is E2 direction? Minus k cap, okay, downward. So for 2D there is nothing along E2, but there is a field which I want to make a mention called 2D 3 component. I did tell you about when I was doing the examples. So it is only function of x and y, but there is a component along minus g. So that is along U2. Okay. So for 2D 3C is only function of kx and ky, but it has component along E2 direction, which is downward in that direction. Okay, but let us not worry about it. Right now we will focus only on 2D 3C bit later. So let us look at this picture. So now this is in xy plane. So this is why it was a problem. It was not able to port this picture. So this is my vector k, and this is my vector u is along that direction. Okay, along E1. But what about minus k? my E1 will be in that direction. Remember I said E1 is switching sign, and E2 does not switch sign, E2 is downward. We need E2, so please keep in mind. So I am going to come make an example where I need E2, and E3 is of course changing sign. So this is under parity when you go to k to minus k. So this one, so U1 is only. So I would recommend that please write like this, even though it is more writing, but especially when you have minus k, then this writing is useful, which I skipped here too, but normally be careful, you write the argument. And what about x component, y component? So it's straightforward. So what is this angle? So this angle is phi. So perpendicular to this is that. So this angle is phi. So UK. So this is minus. No. So ux is minus u1 sin phi. No. Ux is, yeah, ux is in the, this is ux. Okay. So ux is positive. Ux is positive. U1 sin phi. So this is my ux, and my uy is this, which is minus because my positive y is in that direction. So minus u1 cos phi is that one. Okay. So you can always get ux and uy given u1. So many times you will be given Cartesian vectors, and you will need to convert u1. You will need to get u1, or given u1 I need ux and uy. So especially the problems which you are doing in the last class. So we were having ux and uy, right, the homework problem. Now I need to solve in Kriya-Haring, then I need u1, so I need to convert it. Okay. So this is introduction to basis function and how to get from what do they mean, how to get energy, how to get helicity. Okay, so we stop. Thank you.